So thanks for the opportunity to present the last 4.5 years of work we did on the GEMS project, and I'm going to show you some key results. So it will be just Simone and myself presenting, but I'd like to emphasize there was a large team of people that contributed and worked on this project. So the GEMS project was really a collaboration between Durham University and the British Geological Survey with a number of project partners. And I'm not going to talk you through all the names and organizations on this slide, but just to illustrate that it's actually a team effort. So the GEMS project basically was aiming at tackling a number of key challenges in mine water geothermal. So, for example, efficient heat extraction, looking at heat storage, looking at social acceptance and regulations policy and the economic viability of mine water heating. So the first three I'm going to discuss quickly in the next few minutes, and then Simone is going to spend a little bit more time on policy aspects later on. So the first challenge is efficient heat extraction. So in many cases, we need to re-inject the mine water that we pump up to get the heat out. And the problem with that is that it might risk thermal breakthrough. So when you inject the cold water, it might flow straight back to the abstraction point, and then you can't extract any more heat out of it. What we want is a slow pathway, a long pathway, so that the water can thermally interact with the rocks and reheat as it gets to the abstraction point. Ideally, you would like to find out whether a mine system is suitable or not before you start the expensive drilling projects. And therefore, we developed a modeling tool called GEMS Toolbox to kind of investigate, to a first investigation of whether a mine system is suitable. The problem with modeling is that, and this was pointed out earlier in previous talks, is that there is a lot of uncertainty. Uncertainty in, for example, the accuracy of particularly older mine plans, and whether galleries have been backfilled, which is often not on those mine plans. And probably since the closure of the mines, some of the galleries will have collapsed. There's also significant uncertainty about the hydraulic conductivity of the several aspects of the mine system, so how easily water is flowing through the system. The way we try to deal with this is that we develop this software tool by using simple conservation of mass and energy and using semi-analytical solutions. And that provided us with a fast enough code so that we can run many different scenarios and explore a whole range of different scenarios using kind of Monte Carlo style investigation. So just to give you an example, recently we tried to investigate what the effect could be of collapsed galleries in the mine system. So this is a hypothetical mine system, a simple example: injection at the blue dot and abstraction from the yellow dot. Water is going to flow through the system, and in this case, the system had galleries which are partly collapsed, which is the blue parts in the bottom plot here. This partial collapse was done completely randomly. So this is one scenario, and this is a second one that gives you a completely different flow field and different amount of heat abstraction. And a third one, all kind of similar, but with a different random collapse of the mine system. So you can run many different calculations. In this case, we ran about 500 or so of these calculations. And that gives us an idea of a distribution of possible scenarios. So in this case, a distribution of the expected abstraction temperature of the mine system. So even though it doesn't give you a precise number, it gives you a range that might probably be useful. You kind of quantify the uncertainty that we have because of the uncertainty in the mine systems. And I guess that might be useful for attracting investors to mine water systems. We also did a couple of experiments at the UK GEOS side that Vanessa was just explaining in an earlier talk. In this case, we compared the observations on the right with some modeling that was done at the BGS. to kind of see if we can learn about fluid flow and heat transfer times in typical mine systems. So quickly going through some of the other challenges. So one of them was trying to look into heat storage. If we want to use heat that is available in the summer, at winter time, we need to store the heat in between. And we have then the option of either going for overground engineered heat storage systems that use chemical heat storage, or use the mines themselves as a heat storage system. So the engineering department at Durham tried to come up with a scheme that kind of combines the two. So the idea that if you extract heat from the summer into a tank with silica gel that absorbs the heat and as a consequence releases water vapor that is then condensed. And the heat from condensation can be added to mine systems in the summer. In the winter, you reverse this. So you take the heat from the mine system, use that to evaporate the water again, inject it into the silica gel, and that releases high-grade heat that can be directly used into homes. Thirdly, we looked at social acceptance of mine water heat, or more the green energy transition more generally. And the aim was to understand the social conditions here. And for that, one of the postdoctoral researchers at the GEMS project relocated to one of the former mining communities in County Durham, and did lots of observations and semi-structured interviews to kind of learn and understand the viewpoints of the communities. And some of the findings that were coming out of that is that those communities, the community was fairly unfamiliar and a bit skeptical about the green energy transition. Communities are therefore also unprepared to take this step, and that providing information and having consultation with those communities is essential to kind of smooth the implementation. On a related project, the business school at Durham worked on looking into what people would choose if they have to replace their gas boiler, using so-called choice experiments and the concept of willingness to pay. So to explain this in this slide, they had about 1,000 people. They gave them choice cards, and one of them is shown here on the right. The choice cards has several options for different ways to replace their gas boiler in the future. One of them being a geothermal solution. And with that comes several different costs and benefits. And asked the participants which of the cost and benefits they valued most. And replacement period was the number one concern for them. And from that, they asked them which of the solutions they would opt for. And the diagram here on the left shows that almost half of the participants suggested to go for a geothermal solution. So that was a whistle-stop tour across the GEMS project. So we had several challenges that we wanted to address. More details can be found on the GEMS website or using the QR code shown here. So some key conclusions were that we developed a modeling tool to look at pre-drilling assessment of mines for mine water heating. We developed a novel heat storage mechanism, and that community interaction is essential for providing the info for implementing a green energy transition. So I'll stop here and then stop sharing and hand over to Simone, who's